Welcome to part 2 of my two-part video series on the inspection and rebuild of first generation Gotway 84-volt Nikola control boards. At the end of the last video, I basically suggested that we had one more test that we wanted to do regarding temperature control solutions for the Nikola board. And that one solution, not a big surprise, is thermal paste, something that is universally lauded by pundits on forums and universally hated by manufacturers. So let's go out to the lab and get an idea what thermal paste can do for us. Now, one of the issues that you'll have when you're using a thermal grease is that the mating surfaces of the MOSFET, when pushed down onto the metal heatsink, will cause a direct short even if you are using a substance that itself is not conductive, because the high parts of the metal will touch when the screw is torqued down. So the need for electrical insulation is still there. So one of the reasons why this test was delayed from the other test was that I did not have this one small essential piece. It's a little hard to see this thing, it's in here. What this is a mica insulator. Mica is used because it's stiff, it's a great electrical insulator, and it's a pretty decent thermal conductor. It's somewhere, it's somewhere in about, I guess, the, I could be wrong on this, so don't quote me. I think it's about a 0.8 watts per meter Kelvin. Which is pretty decent. It's a little bit on the order of something like glass, which is actually a pretty good thermal conductor in thin layers. What makes the mica work really well is that it's extraordinarily thin, much thinner than a thermal pad will be. So what we do in this case is we use the thermal paste. In this case, what I'm going to be using today is a high performance thermal paste, Noctua NTH1. It's a pretty good expensive paste, and the purpose of the paste is nothing more than to fill in the microscopic gaps or bumps and hills in the metal of both the heatsink and the and the back of the tab of the MOSFET. Although it may look very smooth, in reality there's a lot of little bumps, and where there's indentations in that metal, there's air, and air is a very poor thermal conductor. So you just want a thin enough layer of grease that you end up filling in those gaps, not so much that you're floating on the grease. So thermal grease is a little bit difficult to apply. If you apply too much of it, it actually works rather poorly. If you don't apply enough, obviously it doesn't really do anything. It's also quite messy, it goes all over the place, and it's generally toxic. So there's a lot of reasons why people avoid using thermal grease except in applications where it's absolutely necessary. So one of the things that we're looking at today is to find out whether this is one of those applications where it just works so good you can't not use it. Now personally, I am hoping that this doesn't work that much better than the thermal silicone pads, because it is such a pain to work with. But still, I'm going to get set up to to apply some thermal grease to this MOSFET, apply the pad, put a little bit more thermal grease on top of it, and mount it up onto the aluminum heatsink. So during this operation, what I'm going to be doing is I'm going to be placing a number of dots of this material, not attempting to smear it all over, just putting some dots. The idea basically is the material itself will spread quite readily under pressure, and so we don't actually really need to put massive amounts of this material on. I haven't worked with this particular paste, although the consistency of it seems very constant. That's probably a little bit too much I'm putting on there, but I think we'll be able to squeeze it out through the gaps. Let me get a little more out of there. This is probably a great abundance of paste. So I'm just going to leave it at that. We're going to put the paste aside for a second. And I'm sure there's going to be a tremendous amount of squeeze out of this because I did, which I usually do, end up putting too much of it on. So next thing I'm going to do is I'm going to attempt to get this MOSFET, this mica pad, and get this basically in place over the FET, which, as you imagine, is a relatively fidgety job. And in this case, because we want this to be able to be workable, and you can see that this paste does smear out quite well. That's what it's supposed to do, and I think it does it quite well. There's probably a little gap up there. I'm just going to move this around just a little bit to make sure that we're actually getting ridiculously good coverage, because we can. Once again, the fact that this paste is electrically insulating has some advantages to us. Specifically, the big advantage of it is that we don't have to worry if it pushes out a little bit. We don't have to worry about it touching something and shorting. Whether it might be the head of the screw that we're using to install this or something of the kind. But at this point, basically, I think that that's probably a good start there. Now, next thing I'm going to do is I want to get the screw mounted through this, because otherwise it's probably going to be super hard to do that afterwards. So I'm going to get that set up. So at this point, I've installed the mounting screw. As before, the insulating plastic washer is also installed through to keep it from shorting, keep the screw from shorting against the body of the MOSFET. And as you can see, the paste will not create a problem with the mounting screw because the paste is not electrically conductive. So in order to complete this pairing now, we need to do the same thing on the other side to be able to put some dots in the material around in order for us to have also a good contact with the aluminum heatsink. Now, just something that you can't see from the, I can be a little sloppy on this side, I think, and we're just going to torque this down pretty good. So I think at that point, if we have a little bit excess on here, I don't think it's going to hurt us too much. Because we should get a good squeeze out on all sides. By the way, this stuff, it sticks pretty well to the surface. So it's a massive amount I put on there, probably way too much. By the way, I'm not a great fan of working with this stuff, just to let you know. But on the other hand, if it works, I'll go for it. Now, I'm just going to do a little, just a little demo for you here. That if I just take this piece up with the tweezers, I'm going to try to grab it here with the with the place. Now, at that point, one of the things we might be looking at here is, it's not terribly unstable. You see, I can turn it upside down, and nothing really amazingly ugly happens, like it falling off. We can, if we it will shift a little bit on the surface. It's actually really pretty good. You see, if I hold on to these things, I can move that surface a little bit on there. It doesn't have to be perfectly aligned, but it doesn't want to, totally twist around or something. So it's going to be a little bit fidgety if we wanted to assemble something like a Gotway Nikola completely with this. But what I'm going to do here now is I'm going to take this and I'm going to reverse it and get it in position to mount it on the heatsink. Just have to go out of frame a minute here to get this around. Yeah. So basically, this would be in here. Now, this would be somewhat of a different operation if we were working with the actual board, because these MOSFETs would be permanently installed, and there would be a stable working surface on it. But on the other hand, is it as easy as using the self-adhesive tabs? No. It's just plain not. So at that point, I'm going to try to get this screw started and just put my hand down there to stabilize this, and I think we're going to be good to go. Looks like our alignment's pretty good. Okay, so we've got that mashed down there pretty well. As you see, there is some excess paste that is around the board. This is actually not really a problem, except it looks ugly. We also could dab some of that excess paste off, but it's not conductive, it's not going to drip, it's not going to melt, so I don't think that we have to worry about it too much. So with that being said, I think we're ready to do a little thermal test on there to see if this is worth the effort. Well, as our first test, before we do anything involving heat, the first thing we have to make sure is that the body of the MOSFET, which is of course this mounting tab, which is electrically connected with the drain of the MOSFET, which is the middle lead. We would have to make sure that this is actually isolated from the heatsink. See if you can read the meter there, we can see if I go from the screw, which is screwed into the metal, we'll see we're going to get 0 ohms. So we don't want to get that if we go to this lead, which I wouldn't expect that we would. At that point we're getting overload on that, which is infinite ohms. And we could also even sneak in on the side here, to actually touch the tab and see also we have overload on that, and even touch into the grease or the mica pad, and all that basically is going to be insulated. So what we have is we have good electrical insulation, which is necessary for this to make any sense whatsoever. Now we're going to do the temperature test in a similar fashion. We're going to be running for 1 minute and 30 seconds. We're going to be using the infrared thermal probe to determine what the body temperature of the device is, basically going from like the heat sink to where the body is and trying to avoid the leads. To couple into, couple heat into the device, we'll be using a hot high capacity soldering iron, and we'll begin this test and then start the timer, and then I'll jump in with the probe so we can see how we're doing. So the first thing we're going to do here is we'll get this set up so we can get good pressure on the leads, and we're going to come in relatively tight so we can do that. Okay, so we're getting good pressure in here. I've now started the timer, and I'm bearing down with a considerable amount of force in here, and hopefully we can get the this monitor in there so it's showing us what the temperature is doing. So I just tested this a moment. This was running room temperature around 24. We're seeing some temperature elevation in there. Try to move this so you can see it a little bit better. We're seeing some pretty low temperatures here, I would say. We're at 1 minute and we're sitting here at like 35 degrees C. This is really working very well. We're at 1 minute 24, and this is just laughing at this soldering iron. We're way over 1 minute 30 already, and we're sitting at 35 degrees C on this. I almost don't believe this. This is amazing. Getting a little bit hotter here, but not really much. I'm going to go to a full 2 minutes on this, and this is a lot of heat we're putting into this junction. And we're basically cracking 40 degrees. Let's see how fast this actually goes down here. And look at that puppy go. 34, 33. It's just dumping that temperature like crazy. And as typical with this pattern, the Once the temperatures get a little bit lower, it doesn't drop as quickly. So that is really amazing performance. So it's hard to walk away from something like that if you can do it. And we'll do a little bit more discussion of this later. Well, now that we've been able to see the performance of the thermal paste together with the mica insulating washer on the same heatsink with the same TO220 packages, I guess we have to ask a question. Does this change the decision process as to how we might want to reassemble this Nikola? Yes, I think it does. The performance of this setup that we just tested right now that involves as the first step in the reassembly of our controller board, we will need to remove any glue residue which is remaining on the MOSFET's surface. We really don't want any of this on here, as described earlier in the first video. The MOSFETs on this particular Nikola board were relatively clean, but there's still a lot of remnants on there. To take this off, we are going to be softening up the edges of the glue using a heat gun. In this case, we're using like a relatively narrow nozzle heat gun, and we'll just be heating this not enough to melt the glue, but enough basically to loosen it from the edges, make it a little bit softer, and we'll be able to pretty much just kind of pull it off with a fingernail. So let's get to that. So now we're going to get this process started. I have the gun hitting the MOSFET over there, and what we're really going to be doing in here is just kind of like not letting it get ridiculously hot, just kind of like reaching in there and just kind of getting some wads of this off. We could use a tool for this. It's probably not necessary, and I think it'll be a somewhat cleaner job if we just have a little patience and work at it. If we get it too hot, we're not going to be able to use our fingers to do this. But the technique that I'm using is just this, just basically getting a little heat in there and just pulling the pieces off. And I'm going to actually go and finish the rest of this job, which is going to be done exactly like this. But I'm going to get myself a little bit better angle by turning the camera off. So I just wanted to show you here that at this point I've actually switched over to using a pair of needle nose pliers and getting this somewhat hotter than I had originally started to, which I found made it a little bit easier to get a good release point on it, like you see right there, where the pieces are coming off a little bit more intact, which makes the job easier. By the way, this is a really good example of why you should not put glue or any other type of substance on the thermal surfaces of a MOSFET, because otherwise some person, in this case me, is going to have to take it off, or a wheel will burn out or something bad. So I'm going to continue working on this thing, and I'll be back in a minute. So at this point I've finished the job of taking off the excess glue. I don't know whether this is going to come out that well in the camera, but if you see in the palm of my hand, this is the pile of glue that came off these MOSFETs on my board. And if we recall, compared to the boards we had seen previously, the board on this particular Nikola was pretty sparing on the glue. But as you can see, it's a significant amount that was on here. So at this point, we're ready to move on to a better surface cleaning before we continue the made-up process. Now that we've cleaned the surfaces of the MOSFETs, you can use a commercial solvent. In this case, I used a commercial product called Arctic Clean, which is purpose-built for this. Other solvents I'm sure would work fine. At that point, the surfaces were wiped clean with a lint-free paper towel. Anything that you have which is sort of lint-free. I mean, low-grade commercial toilet paper actually works quite well for that. Where more of the rough paper towels that are non-pilly. But basically, when you're done, it's good to take a loop and to get in there and actually inspect to make sure the surfaces are clean of all contaminant and there's no lint or anything on there. A little bit isn't really going to kill you, but on the other hand, you might as well get the surfaces as good as possible. So at this point now, I've gone through and inserted all of the hardware into each of the MOSFETs from the top of the board. I've left out the four corners, and you'll notice in the four corners, basically, I have inserted a specialized tool. This is a fibrous biologic alignment drift, sometimes generally better known as a toothpick. And you can see basically, surprisingly, these have a lot of uses in electronic assembly. It's a little embarrassing, but true. But basically at that point, so we always have a lot of toothpicks around. In the meantime, the idea of this basically is that we could use those tips to align onto the heat shield, the heat sink, and basically be able to put these holes through there and walk the board up slowly onto the heat sink so that we don't cause any smearing or anything. And then we get a couple of the bolts into the heat sink, and everything's pretty much aligned, and we can complete the job at our leisure. So at this point now, we're going to get set up to apply the paste. This is going to be done in a similar manner in that we've demonstrated in the video where we tested the thermal paste and mica insulator combination. The thermal paste we're applying is the same Noctua NTH1 paste that we used in the bench demonstration of the thermal conductivity of the system as we're installing it now. And we're going to apply it in a similar way. We are going to be applying a little bit more of this paste than you would sometimes use in something like a CPU application. The reason for that being basically is that we're looking to make sure we have full coverage. We're not too much worried about squeeze out, and we're not using a spring clip. We're actually using a bolt that we're tightening down. So basically we can pretty much guarantee that the layer remains extremely thin of the paste. But we don't want to go crazy either, so I'm just going to start in that process here. And what we're really doing here is just putting some dots of the material down. I'm going to brace my hands so I can get a little bit better, have a little bit of squeeze out there. What we're doing is just getting a little bit on there. I think I don't have quite enough paste out there. There we go. Okay, so we're just going to be putting some dots on there. I've seen people that actually would take this and applicate it through the whole system. I don't think it's really necessary to do that, but we do want to make sure that we get enough for full coverage, but too much squeeze out there. Like I say, if we go a little bit too far, it is going to all end up squeezing out the sides anyway. As discussed previously, this paste is not electrically conductive, so if it squeezes out to the edge, it's not really going to do any harm. For example, even though this bolt that we're dealing with here is actually going to be going directly into the heatsink, this paste will not cause a short around this. So that's definitely too much paste, but that's the start of it. So I'm going to go back and do the rest of these pastes, and then we'll pick it up from there. We've now finished applying a mica insulator to each of the MOSFETs to prevent electrical shorting, and we're now going to do the final stage of the application here, which will be putting another layer of thermal paste on the heatsink side of each of the mica insulators. And basically, to give you an idea of this, we're just going to be doing a similar type of thing. We're putting some dots on there. I'm actually going to take this with the toothpick and go through and smear that around a little bit. But just to see the basic idea of this stuff, and this paste that we're dealing with is really quite thick. So it's it basically doesn't want to move around all that much, but that keeps the mica insulators pretty much in place. So I'm going to go do a coating of the rest of these things, and then we'll take it from there. Okay, now I've done an application on all of the individual MOSFET surfaces. I ended up breaking down and using another one of our fibrous biologics, to go through and spread out the paste a little bit, just because it's an irregular surface, and I was a little concerned that even though we'd had a lot of squeeze out in the side, we might not get like around the sides of the mounting bolt. So I figured I'll go through and do this. Now the next step we have to go to is to put an electrical insulator between this layer of of thermal paste and the next layer of thermal paste that mates to the heatsink, to keep the heatsink from shorting directly to the pad of the MOSFET when the screw is torqued down and it goes metal to metal at the high spots. So so I'm going to get the insulator and we'll take it from there. So these are the extremely thin mica insulators that we use. The mica is not a terrible thermal conductor, but more importantly than that, these are incredibly thin. And so what we do on each of these is really quite simple. We just basically make sure the screw's in position, and we take a mica insulator and put it through the screw and over each of the MOSFETs, lining it up as best we can. And one of the things you'll see with this, if we line this up and press this down just a little bit, it sticks rather tenaciously to the MOSFET. So basically at this point it's unlikely to move as we spread the next layer on it. I probably could have done a slightly better job of getting that down, but you can kind of see the idea. They are a little bit oversized, so if the fit is not absolutely perfect, it's still just going to be fine. So that's the next step. So I'm going to go back and finish the rest of the MOSFETs, and we'll take it from there. Well, we've now completed applying the paste to the to the heatsink side of the mica insulators, and all of the hardware is in place. And from where we are right now, everything looks like it's about ready for the board to be mated to the heatsink. As you can see, we still have the toothpicks inserted, which will be which we'll use as a drift to to guide in. And once at that point we get down onto the heatsink, we'll be able to take a couple of the screws and be able to put them in, and we'll just work around. And then at that point we'll have to put the four corners in place. In this particular case, the three of these corners, this one, and that one, basically are bare and do not have the electrically insulating collars that we're going to have to install. So I'll have to remember to put those in. This one down there, it turned out to be, it was kind of locked in by a piece of silicone during manufacturing. So since it wasn't hurting anything, I left it in. But it's extremely important that two things happen. We make sure that we have a mica on each of these MOSFETs, extremely important. And the second thing is that we have an insulating collar in each of these screws that are going to be going into the heatsink. So we'll be taking one more look when we have on that. So at this point I'm going to get the heatsink, and we're going to I'm going to set up to do an alignment. So I've moved the camera to the side a little bit, so hopefully you can get a slightly better view of what this assembly operation is going to look like. And as we see, we have these banks of I have to bring the shield over a little bit so you can see it, but the heatsink. So we'll see, basically we do have a row of these holes that are coming through from the back here, and basically we have to align those up with the toothpicks that we're using as a drift on this. So I'm going to basically lift this up and put this into position. By the way, as this is a very good time to go through and make sure that all of those micas are square to the MOSFETs or relatively close. The alignment certainly isn't going to get better than it is at this point. I'm also going to take the opportunity here to just do a little bit of wipe up of this corner here. Basically, as we discussed before, this material is non-conductive, but on the other hand, it's nice to be sanitary and not have splash out all over the place. Well, our alignment is looking good now, and at that point we can continue the operation by putting in the extra hardware sets that we left out because we were using the toothpicks for alignment. Well, at this point now we've gotten all of the hardware mounted into the board, making sure that we have the isolation collars in all of them. We're going to do a little bit of a quick cleanup around the edge of the board, just taking away a little bit of this squeeze out that we have in there, and they're probably going to be a little bit later, so I'll probably do a slightly better cleanup just so that it's not a mess as we're working with it and putting it back in the wheel. See, I'm just thinking now. I think basically the things have worked quite well. One of the very nice things about this, quite frankly, is that if we look down, if we sight down the rows of the MOSFETs, we can clearly see the micas and make sure that all of them are square and lined up underneath the MOSFET the way they should be. We have very good visibility on that. More so than I expected, so that's a really good confidence boost to make sure that nothing is kind of twisted around or shifted in the process of assembly. So I'm going to go ahead and tighten all these down and take it from there. At this point, I've gone through and I've torqued down each of these MOSFET bolts at this point that go down into the heatsink, and at that point all of them are quite tight. And after putting all of the screws back in and taking all of the hardware that was secured with the silicone and reapplying silicone for security, the board is back in. Thing of beauty. Look what we have, a wheel. So after reinstalling the board and buttoning everything up, we have now a restored fully functional 84 volt Gotway Nikola. Just had this out for a little ride out in the parking lot and everything seems real good. Is it any different than it was before? No. It's exactly the same as it was before. It's a great wheel, rides well. I'm not expecting to see a lot of changes here. Potentially I will be watching the temperature on more vigorous rides. And I'm not really quite sure whether the temperature is going to be showing a higher temperature or a lower temperature. My guess is it might actually be registering a little higher because all of that localized heating that might have been there from the previous solution is all going to go directly into that big heat sink, and possibly this is going to be registered more on the temperature sensors on the board. If you wanted to ask my guess would be I'm not going to see any difference at all. So the question that could be asked, is there anything actually inadequate about the original design of the Gotway Nikola control board? And I think the best answer is I would say yes and no. I would say no in that if the board was assembled the way the engineers at Gotway wanted it to assemble, I think probably this wheel will probably take almost anything you're going to throw at it. I would say yes, there is a problem, because my feeling is when you use the small surface area packages of the TO220 packages rather than something like the TO247, I think you create a situation where you're a little bit more sensitive to your thermal solution. So if you're using slightly less expensive components, which in a consumer product you would want to use, or something that's less labor intensive, which certainly using the pads that Gotway was using rather than something like thermal paste, which is very, very difficult. There's a really important reason why you might want to use a solution similar to Gotway did, and if the board is designed correctly and tested correctly, there's no reason why you can't use a solution like this. I think we went through this exercise just to kind of show what you can do and whether this stuff makes a difference, and the answer is yes, it definitely does make a difference. So with that, I'm going to conclude this video, and thank you for watching.